So thanks to those folks. So I'll hand over to Dylan in a moment to tell us all about the workshop. Just a few logistics. You've discovered the food and coffee outside. That'll be there for the breaks. For lunches, you're on your own. There are lots of options on and off campus. Please don't bring food and coffee into the auditorium. Water is fine, but we like to try to keep these spaces clean. At lunchtime, if you want to leave stuff in lockers on the far side of the building, there are lockers that work with PIN codes. You can use those. So we're working with a hybrid format over Zoom, and our videographer Omid Farr is going to be helping speakers, hooking up computers and microphones and so on. And a big thank you also to Keilani Penland, who did all the local arrangements for this week. So let's thank her.
All right. Yeah, so thanks a lot for joining us for the workshop on multi-agent reinforcement learning and Bandit learning, right? This is the last workshop of the Learning in Games program. So I'll just say a little bit about the topic and kind of what we have planned. So, multi-agent reinforcement learning, it's a very rich topic, and it's a topic that's been explored through many different fields over the years, right? So the foundations kind of go back to the work of Shapley in the 50s. And since then, we've seen it explored throughout, of course, like game theory and econ, but also theoretical computer science. And, most recently, AI and machine learning, right? Both on the empirical side, like say in the context of DeepRL, and also even more recently in learning theory. And so, given all this excitement, the goal of this workshop, it's kind of twofold, right? So on one hand, we want to highlight the most exciting recent developments. And on the other hand, we want to try to kind of pin down, what are the most important questions and problems to solve for research going forward. So we have I think a pretty interesting program planned. And, we're lucky to have some pretty great speakers kind of with representation from all of the topics I was mentioning before. And just a few of the kind of themes and topics we'll cover, include like, okay, so sample complexity and learning theoretic guarantees, computational complexity, communication, coordination, connections to say like game theory and control theory, and also empirical research, right? So like DeepRL. Okay, the last thing I'll mention here before we kick it off is just, okay, in line with the theme of trying to like pin down, open problems and questions, the last session of the day tomorrow is going to be an open problem session. So, if you have problems you're stuck on or that you'd like to see solved or collaborate on with other people, you should come and give like a little presentation. This is going to be super informal, so you don't have to make slides or anything. You can just give a Blackboard talk. And yeah, I'll make a little like sign up sheet on the whiteboard after this, in case anyone wants to sign up. Okay, I think that's just about everything I want to say about the workshop. So why don't I go ahead and kick it off? And so to start us off, we're really lucky to have Sergiu Hart here, who's going to be telling us about calibration and connections to game theory.
Okay, hello. Do you hear me?
Yes.
Yes.
Yes. Okay. Since I see only the front row of the auditorium, which means I don't see any faces, and I don't know whether you guys are following anything I'm saying or not. So feel free to shout and ask or whatever. I wish I could give this talk on a blackboard. That's my preferred medium, but well, doesn't work. Okay, so
just real quick, I'll also monitor the chat for questions in case this comes up.
Okay, yeah, because I won't be able to, I think. So if there is anything, you just stop me and tell me, right?
Yep, sounds good.
Okay, very good. Okay, so I want to talk to you about Calibeating, which I guess that's the reason it's in quotation marks. Probably you don't know what it is. You may guess perhaps, but we'll see. So first of all, this is joint work with, well, it's not Guylan, it's Dean Foster. So it's another D. Foster. Yeah. Here are the papers. By the way, the papers and the presentation, you can find them on my webpage. There are links here, or just, just write my name and go to my webpage. And you can, if you care about this stuff, you can find more additional things on my webpage. Okay, so I don't know how many of you, I gave a talk, when was it? At another workshop, I think it was in April, beginning of April or end of March, I don't remember exactly. And in some sense, what I'm talking today, so that was an introduction to calibration, and introduction and new approaches and new ideas and so on. So it's not just, it was not just a review of old stuff, it was new stuff. And I'm in some sense continuing from there. But since even if you were there the previous time, you probably forgot everything about it. I don't remember what I said anyway. So I'll do a short recap and then we'll take it from there. So let's start with what is calibration, okay? So the forecaster says the probability of rain tomorrow is P, okay? Now, as I'll repeat what I said in my previous talk. So bear with me if you heard this already. Once upon a time, forecasters would just say, tomorrow there's going to be rain or tomorrow there's going to be sun. That's it. And of course, they were not very good. And people were really ridiculing them quite a lot. Weather forecasting was not something was not a profession that people were proud about, to say the least. As I said, there were cartoons about weather forecasting. I remember them as a kid, before any of you were born, of course. Then at some point, instead of saying tomorrow there's going to be rain, forecasters switched to tomorrow there is a chance of 70% of rain. The chance of rain tomorrow is 70%, okay? Well, and it doesn't rain. Well, it doesn't rain. What do you want? I only said 70%. I didn't say it's going to rain for sure. So it did rain, okay? Now, the question is, can we catch such a forecaster in any way? Or let's put it in a better way. Is there any meaning to this 70%? Now, of course, if it's probability is like the long-run frequency. Right, that's a main interpretation of probability. So to check it, we really need a long time and to see over time whether this is correct. So how do we check it? We do the following thing. The idea is trivial, but it takes some time. If you never heard about it and you think, well, how do I check this 70%? What does it mean? Well, here is what it means. Let's take all the days when the forecast was 70%. Only the days when my forecast was 70%. And let's see how many rainy days there were out of those days when my forecast was 70%. If I'm a good forecaster, formally, this is called, if I'm a calibrated forecaster, then the proportion of rainy days out of those days when my forecast was 70% should be 70% or close to it. In the long run, okay? And that should be true for any 70%, yes? For 10%, 20%, whatever forecast I'm using, the long run frequency should equal to my forecast. Then I'm calibrated, okay? Now, let me start with a result. And let me say, as I said, I know nothing about weather forecasting, okay? I know nothing about clouds, or any of the physics involved or earth sciences or anything, but I know some other stuff, okay? And with some other stuff, I can guarantee that my forecasts are going to be calibrated. Now, not just say in the summer in Israel where it never rains and then my forecast will be 0%, yes? But it's going to be calibrated no matter what place in the world you want to put me, or no matter how the rain is generated. Even if the rain is generated by a rainmaker that, as computer scientists and you guys, computer scientists say, is an adversarial, whose only aim in life is to make me as a forecaster look bad. That's it, doesn't care about anything else. So even against an adversarial rainmaker, I can guarantee that my forecast will be calibrated, okay? Now, that's a great result due to Dean Foster and Ricky Vora. in the early 90s, probably even earlier than 94, which they had a very hard time to publish it, because any journal they sent it to, they will get after 2 weeks a desk rejection saying, come on, you make no assumptions about the weather, this result cannot be true, okay? Well, in the end, it was published because the result is correct. And in fact, there is a very neat proof, very short proof by the minimax theorem, okay, I'll say it, I'm not going to describe it, I'll just say it in one word. Suppose that I knew, so this is like a game between the forecaster and the rainmaker. Suppose I knew the strategy of the rainmaker. What does it mean? Suppose I knew the mixed strategy of the rainmaker, because the rainmaker, of course, may use randomizations. If I know the mixed strategy of the rainmaker, then every day, given the history, I know what is the probability that he will choose rain and what is the probability that he will choose sun. Well, my forecast is going to be that probability rounded up to whatever grid I'm working on. So if I know the strategy of the rainmaker, I can obtain calibration. That's quite trivial, yes. If I know the probabilities of rain, of course I can give calibrated forecasts. The minimax theorem then says, because the whole game is finite, we are talking about a finite horizon, finite grid, then the minimax theorem says there is a strategy that guarantees calibration no matter what the rainmaker does. Okay? Very nice result, very neat. It's, in my view, it's a beautiful use of the minimax theorem. By the way, in computer science, that's what's called the Yaw's principle, okay? That's a minimax theorem, von Neumann's minimax theorem, okay? The question is, how do you do that? So, by the way, there were lots of other proofs. There was the original proof of Ostervorath, proofs by Fudemer and Levin, and lots of other proofs of this result. It's such a striking result that, people really want to find ways to convince themselves that it's true. Then there is the work of myself and Andrea Mascolel, where we found a nice way to guarantee calibration using black hole approachability. This was simplified further by Foster. Now, when I say Foster, it's Dean Foster, yes? Sorry, Dylan, you are not yet on the scene. So Foster is Dean Foster, yeah? And then, in fact, in our previous paper on forecast hedging, there is an even simpler procedure, which I'm going to describe it to you. It's so simple that, I'm going to describe to you what it is. So here it is. So let's draw a picture where on the horizontal axis, we have the forecast. And on the vertical axis, we have the average frequency of rain. Okay, it says average action, but the frequency of rain, okay? So perfect calibration means that, so if I take, for example, let's see if I'm trying some new technology with my iPad and something, so let's see if it works. So if, for example, I take here, oops, well, I think I need something, sorry. Okay, if I take here, oh, it does work. Let's say I take this, the 20% forecast. Then what do I want? I want the frequency of render to be exactly 20%. So it means that I should get this point. And the same thing for anything that I'm using, okay? So perfect calibration means that my graph is going to be on this diagonal, okay? Very good. So let's just make life easier. I just took 6 different forecasts, at the 20% just for the picture. And now I'm at a certain day. So there is some history, and that history gives me this graph, okay? So each dot here represents the average frequency, the frequency of rain for each one of the 6 forecasts, 0, 20%, 40%, up to 100%, okay? Now, those dots are arbitrary. I mean, they come from the past. Yes, I don't know what they are. Okay. So here is what I do. I have to decide what to forecast tomorrow. So here's what I do. I find 2 points, one above the diagonal and one below the diagonal, join them, and forecast exactly the intersection. How do I forecast the intersection? I'm forecasting those C1 and C2, those 2 points, with probabilities that on the average give me exactly the point when they intersect the diagonal. Now, how do I know that there is 1 point above and 1 point below? Well, the 0%, okay, it must be that the frequency of rain is positive, right? So it must be above. On the other hand, now what happened here? Okay. Sorry. Well, doesn't seem to be working the way I expected. Okay, never mind. On the other hand, for the 100% forecast, I must get the dot which is below the diagonal. Okay, so if I start above the diagonal and end below the diagonal, then I always must cross it. So I find two adjacent points when one is above, one is below, and I forecast that thing. That thing works. So the procedure is extremely simple. Okay, I just keep this graph and keep updating every time what happens, and find 2 points like this, and I'm forecasting either C1 and C2 with the corresponding probability, so that the average is exactly the point where it intersects the diagonal. Okay, the fact that it works, well, the proof takes a little work. Okay, it's not completely trivial, but the procedure is extremely trivial. Can't be any simpler than that. Okay, very good. Now let me just show you, before I get into theory and so on, some nice pictures that I took from the web. 538.com, that's Nate Silver's website. So they publish some calibration plots, which are exactly, the horizontal axis, what they forecast, on the vertical is what happened. Okay, you see? Now you see that for sports, they are pretty well calibrated. Almost everything is very close to the diagonal. Politics, a little less, Politics, there is more variance over there. Another one is electionbettingodds.com, okay, where again you can see that perfect calibration is the blue line, the diagonal, and what they really got is something that is not far away from being calibrated. Now, as I said, should we be surprised by that? Since there are simple procedures that guarantee calibration, no matter what, we should not be surprised. Now, do they know anything that we don't know? Maybe, maybe not, I don't know. Anyway, that's just to show you something from the real life. Okay, now let's take a very simple example. Now I'm moving on. Okay, so that was background. So let's take a very simple example where we just have rain, no rain, alternatively on alternating days. Okay, so day 1 rain, day 2 no rain, sun. Day 3 rain, day 4 no rain. Assume that we have such an occurrence, okay? And I want to look at 2 forecasters. Here is forecaster number 1. He says on day 1, 100% chance of rain. On day 2, 0% chance of rain. Day 3, 100% chance of rain. Day 4, 0% chance of rain. I mean, this guy is perfectly calibrated. I mean, he exactly tells us what's going to happen. But let's take another forecaster that says every day 50% chance of rain. Is he calibrated? Answer, yes, he's calibrated. Now, why is he calibrated? Because when we look in the long run over all the days when he said 50%, which is all the days, half of them were rain and half of them were not rain. So the frequency of rain in the days when he said 50% was indeed 50%. So he's calibrated. Now, clearly, F1 and F2, F1 is very useful, F2 is not very useful or much less useful. Okay, it really doesn't tell us anything, just tells us a long run frequency. Okay, and again, it works because in this example, we had this 50% long run frequency, which doesn't have to happen in general. Okay, so calibration for both of them was 0. The calibration score, I mean, yes, say calibration, I mean the calibration score was 0 for both of them. But clearly F1 is a good forecaster, F2 not so good. How can we capture that? So here is a neat way to capture it. Calibration essentially is a binning operation. Binning means taking things and putting them in bins. What are the bins? The bins are the different forecasts. So for F1, we have 2 bins. We have the 100% bin and the 0% bin. For F2, we have just 1 bin, the 50% bin. So F2 takes all the days and puts them in 1 bin, the 50% bin. And that bin is okay. The average in the bin is 50%, everything okay. F1 takes all the days and puts them into separate bins. The odd days, when there was rain, they go into 100% bin. The even days, when there was no rain, they go into 0% bin. Okay? Now, what's the difference? The difference is the variance inside the bins. For F1, the beans have no variance. All the days in the 100% bean are the same, rain. All the days in the 0% bean are the same, no rain. F2, the days that are in the 50% bean, half of them are rain, half of them are no rain. So there is a big variance inside the bean. So the inside bean variance, the in-bean variance is 0 for F1, and it's a quarter, 1/2 squared, yes, because 0 minus 50% or 1 minus 50% is 1/2, yes? So the variance is 1/4, which is big. It's the biggest variance that you can get for 0, 1 unknown variables, of course. So for F1, the in-bean variance is 0. For F2, the in-bean variance is a quarter, okay? So let me just introduce some notations again, because I want to make things clear. Even if you don't follow, you should be able to follow even without the notations, but just, when I hear a talk, I always like to make sure that I follow exactly what the speaker wants. So notations are sometimes useful. So let's call AT the action at time t, which is rain or no rain. But by the way, it could be something more general. This could work in an arbitrary Euclidean space. Doesn't have to be 0, 1, doesn't have to be R1, can be anything, okay? And the forecast at time t, we call it C of t. And then when we take a forecast X, A bar of X is the average of the actions in those periods where the forecast was X. So if the actions are just 0 and 1, that's a frequency of 1, the frequency of rain, okay? And that, of course, we set up capital T, which is our horizon, and it's underlying all the notation here. So the capital T, I'm not going to put it as a subscript, but everything as a subscript capital T, okay? It's the horizon. Horizon changes, then of course everything changes. So A bar of X is the average action when the forecast was X. So if you want the formula, here is a formula, okay? But of course, you don't have to, I mean, everybody knows how to make averages. And what's the calibration score? Well, it's the average distance between forecast and the average action for that forecast, okay? So if you want the formula, here is the formula, okay? So you look at each forecast and you see how far it is from the average of the bean, okay? And you do it at time capital T, remember, okay? So you saw the formula. Then we have another score, which is the variance inside the beans. This is called the refinement score, okay? So we're going to call it R, or R sub T. So it's the average variance inside the beans. You want to see a formula? Here is the formula. You are just looking for each, at the distance between what happened on day T, the action on day T, and the average in that bean, okay? And you take squares, like in statistics, you always like to do variances and things with the L2 norm. By the way, it doesn't matter which norm you use. All the norms are equivalent, but it's convenient to work with the L2 norm. Okay, so that's a refinement score. Okay, now there is another score which is well known. It's a Breyer score. Breyer was a meteorologist, and he gave the following score. He said, let's look at the distance between the forecast and what happened. So you look at forecast, which is CT, action, which is AT, and let's look at the average distance between AT and CT. Okay, and that's a Breyer score. Now, here is something that those who know statistics will not be surprised, but it turns out there is a beautiful decomposition of the Breyer score into the sum of the refinement score and the calibration score, okay? Now, by the way, there are other decompositions of the Breyer scores, but that's one which I think is very useful. And so the Breyer score is the sum of the refinement and the calibration score, okay? You want the proof? The proof is very easy. It's just a famous formula that when you want to know what the expected square distance is, it's the variance plus the distance of the expectation from that constant square. Okay, I hope that everybody saw this. No, it's just this formula. Okay, never mind. But in a sense, the refinement score and the calibration score are orthogonal. Okay, one measures the variance inside the beans. The other measures how far away are the beans from what you said as calibration score, as forecast, sorry, what you said as forecast to the average of the bean, okay? So let's go back to our example where we said calibration is 0 in both cases, and the in-bin variance is 0 and 1/4. So now I can write it as k equals 0 for both of them, r being 0 and 1/4. And so the Breyer score is 0 and 1/4. Okay. So now, as we said, F1 is an expert. F2 is, I will call him an expert, but, you can still call whatever you want. But if you want to check real expertise, I mean, the point is that you should not do it with the calibration score, because both F1 and F2 are going to pass the calibration score. And as I said, I can pass the calibration score without knowing anything about weather. Anybody can pass. Anybody in the audience can pass in the score now that you know the trick, how to do it, okay? So calibration is not the way that you identify experts, okay? The way to identify experts, you should look at the Breyer score, okay? That's one lesson that we learn from here. The Breyer score, again, remember, it's 0 for the good guy, for F1, and it's 1/4, it's big for F2, okay? Now, what is really this expertise that I'm talking about? Well, expertise is somebody that recognizes patterns and regularities in the data, okay? That he knows something and recognizes that. I mean, maybe because he knows, somebody told him something about the process that generates the data, or maybe just looks at the data and finds patterns, there may be patterns there for one reason or another, okay? And when you recognize patterns, then that allows you to sort the days into bins such that all the days that are in the same bin, they are very similar, okay? What happens is those days is similar. That's how you recognize, okay? And of course, you want to make the binning as refined as possible, because putting everything in one bin, I mean, you have not recognized anything. Everything is the same for you. Okay, you have not identified anything. Okay, so expertise is really measured by having a low refinement score. Okay, the variance in the bins should be small. Means you're succeeding in identifying all those days where there is very little rain, all those days where there is a lot of rain, and so on. Okay, now, as I said, calibration can also be guaranteed. Now, to guarantee calibration, you run an algorithm like the one I showed you, or some other algorithms. As I said, there are many other procedures to do it. I showed one that is extremely simple, but there are many other calibration procedures, calibration algorithms. Now, if you run a calibration procedure, then suppose you have some expertise, you know something about the weather, okay? You have some information, you have some knowledge, you have some expertise. If you use the calibration algorithm, that's lost. That's completely lost. Okay, so the question is, can we get calibration, but without losing expertise? Assuming we have some expertise, can we do that? Can we be calibrated, but not lose whatever expertise we have, whatever patterns, whatever things we have observed in the data, can we keep that and gain calibration, okay? So in a sense, can we get K down to 0, but without increasing the inside inside bin variance, the R, okay? Or let me state it differently. Can we take B, the Breyer score, and decrease it by K, okay? That means bringing K to 0, okay? So, sure, we can do this very easily, okay? What we can do is take any bin, look at the average of the bin, and if the average of the bin is not equal to what the forecast that generated that bin, then we can just change all the forecasts for that. We take a bin, let's say the 70% bin, okay, and we observe that the average in that bin is not 70%, but it's 40%. So we say, okay, every time we set 70%, we should replace it by 40%. Of course, what this does, immediately it makes the calibration equal to 0, because now we really are stating the average of the bin, okay? We are not changing the variance inside the bin, because the variance inside the bin is the variance of what happened in those days. It's nothing to do with the forecast. It's to do only with what happened in those days. Whether there was rain or no rain, that generated a certain variance. We have not touched that, okay? Now, of course, all this we can only do in retrospect, okay? What is called offline, okay? We can do it only in retrospect, say, wait a minute, every time I said 70%, no, I meant 40%, okay? Correct it backwards, okay? Now, that's of course not allowed. So the question is, can one do it online? Okay, so can we make this correction online? Okay, now okay, so just to make sure that the game that we are playing is well defined, so we have a certain forecasting sequence BT. Okay, so B sub T is the forecast that is given to us by some forecaster. Okay, and it's the forecaster that we want to beat. Okay, we want to improve. That's why it's called B. Or if you want, it's a bad forecaster. Forecasters that are going to improve. So whatever reason you want for the letter B, okay? We are going to generate a new forecast that we call it CT. So C sub T is our forecast. It has to be online, which means to generate the forecast CT, we are only allowed to use the forecast of the other guy and, of course, the history. Not anything about the future, okay? And what we want is that the Breyer score of our sequence C should be lower than the Breyer score of the sequence B by at least the calibration score of B. So essentially, we have, now, of course, when I say something like this, what I mean is that you put out the subscript T and you say this happens up to some error that goes to 0 as T goes to infinity, and you want this to be done uniformly over all sequences, AT and BT. Those are technicalities that, you know, I guess everybody in the audience, if you work in this area, you know them. But I'm just ignoring them for the moment, okay? So we want our Breyer score to be lower than the Breyer score of the other sequence by at least their calibration score, okay? So our Breyer score is going to be less than the refinement score of the other guy, because B minus K is exactly R, okay? So what we call this is that we are beating B by B's calibration score. And we call this Calibeating. Calibeating is beating someone by his own calibration score, lowering his Breyer score by an amount that equals to his calibration score. Our Breyer score is going to be lower than his, not just lower, but lower by an amount equal to his calibration score, okay, in the long run. And we want to guarantee this for all sequences, okay? So just for a simple example, if somebody, just to make it clearer, let's go back to our RAIN 1010. Suppose the forecast was 80%, 40%, 80%, 40%. You can easily compute that the calibration score of this guy is 0.1 because sometimes he has an error. Okay, I mean, computation doesn't matter, okay? So Breyer score is 0.1. The refinement score is 0 because all his beans are uniform. All the beans, when he said 80%, there was rain. So there is no variance there. All the beans, all the days that are in the 80% bean, there were rainy days, no variance. All the days when he said 40%, no rain, no variance, okay? So how do we correct this? Well, we clearly correct it by replacing 80% with 100% and 40% with 0%, but that is done offline, okay? So that's very easy to do in such a simple example. The question is, how do we do it when we are in a general non-stationary situation? It's not rain, no rain, rain, no rain, this kind of very nice alternating pattern, but it's an arbitrary weather. Remember, even adversarial, okay? So the weather is arbitrary, it's not stationary. The forecast B are arbitrary, there is no regularity there. The beaning of B is not perfect, as it was in the example. The bean average don't have to converge, which means, you know, maybe that if after 100 days, the bean of the 40% was 60% rain, and after 200 days, it's now 30% rain. So these things may fluctuate. There is no reason for those to converge, okay? And we have to do it online. And we have to guarantee it even against an adversary, okay? Can we do that? Answer, yes. Now, if you work in this area, perhaps you are probably not surprised by this result, but I hope that you'll perhaps be surprised by how simple it is to do it. There's a very simple way to do it, yes? By the way, our original proof was, 5 pages with taking some algorithm and modifying and doing that and so on. And then we said, wait a minute, I mean, it can't be so complicated. There must be, okay? And we started looking at it, and in the end, we found really a very simple way to do it. Here is a simple way to do it, okay? Here is a procedure. It's a procedure that guarantees, no matter what the weather will be, no matter what the forecast B will be, that we are going to beat that forecast, the B forecast, by at least its calibration score, okay? And what you do is the following. So here is the formula, and here is in words. I'm now at time t, small t, okay? and I'm looking at the bean, and I'm looking at the forecast B sub t, which is the forecast of the other guy. And I'm looking at the bean corresponding to that forecast, and I'm looking what is the current average of that bean. What is the frequency of rain in that bean? Of course, up to yesterday. I still don't know what's going to happen today. That's going to be my forecast. Okay. Okay. So C sub t, my forecast at time t, is A bar at time t minus 1 of the bean corresponding to the current forecast of the big guy. That's it. That works. Okay. And I'll give you a proof. Let's see. I have about 10 minutes, right? I think I started, okay, 7 minutes or something. Okay. I want to show the proof. It's so simple, but it's neat and it has something to it. Okay, so here's the proof. So let's start with the formula for variance. This is the formula for variance. You take x1 up to x sub t, and this is the formula for the variance. And and here is a different way of writing this formula, which I guess many of you, perhaps all of you, have not seen yet. Well, I didn't know it before I started playing with it. Okay, so notice that the difference between the two formulas is in the original one, we look at the distances from x bar t, which is the average after t period, capital T periods. In the second formula, we look at the average, we look at the distance from x bar t minus 1, which is the average up to the previous period. Okay, those two things, by the way, if you want a nice exercise, prove it. Okay, it's a neat exercise to prove it. It's not something difficult, of course, once you see it, but it's nice. So what it says is that if we ignore the 1 over t factor, which I put in red, then we'll get we can ignore that because it's summation of 1 over t divided by 1 over capital T, which is like log t over t. So that goes to 0 as t goes to infinity. Yes, so it's small o of 1. So we can ignore that. And if we ignore that, then we get this thing that the variance is approximately this expression, which we are going to call the online variance, that looks like the variance, except instead of subtracting, instead of looking the distance from xt to the average at the end, you look to the distance between xt and the average up to yesterday. Okay, so let's call this the online variance. And the difference between the variance and the online variance goes to 0 as capital T goes to infinity, assuming that all the x's are bounded. Okay, now if that is true for the variance, since refinement is really the average of the variances in all the beans, then we are going to get the same thing, okay? And I'll just write the formula. If you remember the formula for R, you have to subtract from A the average of the bean at capital T. Instead, you now subtract from A the average of the bean at time t minus 1 in the previous period. So that's it, okay? Now, what does our procedure do? Our procedure takes exactly this. Okay, let me see if I can. Something happened to my screen. Okay, I don't know, but let me try. Okay, this thing here is exactly our forecast. Okay, so this is really the Brier score of my forecast because the distance between AT and CT is exactly A bar T minus 1 of BT. Okay, so what we got is that RB is BC minus something that goes to 0. Okay, that's it. End of proof. That's the whole proof. Okay, very good. So now let's go one more step. Okay, so we know how to calibrate. Okay, that's a way to calibrate. Okay, you forecast the average up to now of the other guy's forecast, of the bean, of the other guy's bean, according to the forecast that he's going to use now. So if he's going to say 70%, we are going to look at his 70% bean, look at the average, at the frequency of rain that we had up to yesterday in the 70% bean of his, in the bean of his 70% forecast. We are going to forecast exactly that. That's it. It works. Now let's try to do the following thing. Suppose I want to calibrate myself. I want to do self-calibrating. Okay, it's not a new religion. Don't worry. It's but let's see what it says. So self-calibrating means let me give a forecast CT which exactly equals to A bar T minus 1 of CT. Well, if we can do that, what are we going to do? That means that B and C are the same. Okay, I'm beating myself. I'm calibrating myself. Then we are going to get, so we replace B by C everywhere. We are going to get B, the Brier score of C, less or equal than the Brier score of C minus the calibration score of C. Okay, which is exactly equivalent to saying that the calibration score of C is 0. So self-calibrating is calibrating. We just get a calibrated procedure. Okay, so self-calibrating exactly makes calibration score equal 0. Question is, how do we get CT equal or even close to A bar T minus 1 of CT? So look, A bar T minus 1 is a function that maps forecast to the average up to yesterday of the bean corresponding to that forecast. It's an arbitrary function. In fact, are those dots in the graph that I showed you, okay? They can be anywhere, okay? So what we are really trying to find is a fixed point, a point that is on the diagonal of that graph. If it's one dimension, if it's multidimensional, then of course it's a fixed point in RD for a general dimensional space, for a general D-dimensional space, yes? How do we do that? Well, if the function would be continuous, then of course Brouwer fixed point theorem gives us a fixed point, but there is no reason for this to be continuous. So how do we do that? We cannot. Can we find perhaps an approximate fixed point? No, because again, think of a function that is 1 up to 1/2 and 0 from 1/2 on. Okay, and remember, you want to be on the diagonal. I mean, there is nothing close to the diagonal. There is no approximate fixed point. Okay, there is nothing that is even close to being a fixed point. Okay, so we do something else. Okay, so here is the result, which we call it a stochastic fixed point. It says the following: there is a probability distribution over forecast, okay, such that the expression written here is correct. Okay, now what does this mean? Okay, sorry, 1 second. I'm still. Oops. Okay, let me try now again. So if C and G of C were equal, if I had a fixed point, then this expression would be 0. So I'm looking at this expression, and I want it to be small, no matter what X in C I'm taking, okay? So it turns out that I can always find not a point C such that this is true, because finding a point C such that this is true essentially says a fixed point, okay? But I can find a probability distribution over point C such that on average, this thing is small, is less or equal, say, delta square, okay? Now, how do we prove such a thing? Okay, here are the assumptions on C, compact, convex, whatever. For G is an arbitrary function. It's important. It's an arbitrary function, completely arbitrary. Okay, make no assumption on the function. Now, this neat result is a minimax theorem. Okay, if you want, solve a linear programming problem. Okay, but I like to think of it as a minimax problem. Okay, so that's a stochastic fixed point. That's something that in our previous paper on forecast hedging, we called it an outgoing minimax. And if you want more on that, look in our previous paper, look in our current paper. There is an appendix that discusses this. It's a very useful tool, okay? And has to do with hedging, what we call forecast hedging, and it's a very nice tool. Okay, let's forget that. So the result that we get, and I'm finishing, just 2 more slides, and I'm finishing. Yes, I'm sorry that I was too slow at the beginning. So if we apply, sorry.
Oh, I said no problem.
Yeah. Okay. So the result is that if we apply this outgoing theorem or this stochastic fixed point theorem that I said, we can generate a procedure that gives us calibration. In fact, that's one of the standard procedures for calibration. Okay, it's not something new, but it's nice to think of calibration as self-calibrating. Okay, so you just do self-calibrating plus outgoing minimax, and you get calibration. Now, how about the following thing? Suppose we calibrate somebody. So we lowered the Brier score by his calibration score. Our Brier score is lower than his by his calibration score. Does it mean that we are calibrated? No. So somebody can calibrate us, right? Okay, and we can get now somebody calibrating and so on, so you can get this infinite regress. We should stop it. How do we stop it? By making sure not only to calibrate somebody, but we ourselves are calibrated. Can we do that? Answer, yes, very easy. What we do, we apply our calibrating procedure to the joint meaning of what the other guy says and what we say, plus the outgoing minimaps or the stochastic fixed point theorem that I mentioned, okay? So there exists a stochastic procedure that guarantees calibrating and itself calibrated, okay? Finally, suppose we have many forecasters, okay? We can beat them all, we can calibrate them all, and moreover, we can be calibrated, okay? So there exists, moreover, let's look at this result. There exists a stochastic procedure that guarantees simultaneous calibrating of several forecasters and that you yourself are calibrated. Now, there is a stronger notion, there is a weaker notion of calibration called weak calibration, also smooth calibration, has to do with smoothing out the calibration score, okay? Now, there are variants of that have been proposed in the literature, mainly by Dean Foster and Sham Kakade, and in our previous paper, we think we have cleaned that up, and we have another notion that we call continuous calibration, that it's much more clean and easy to work with, that is stronger, that implies all the previous versions. And the beauty about continuous calibration, so continuous calibration is like calibration, except you smooth out the score, okay? I'm not going to get into details because I'm out of time, but the beauty of that is that you can get that with a deterministic procedure, okay? So if you want to, where is my, sorry, okay, I think here I'm missing something. Yeah, okay. So if what I meant there is continuous calibration, okay? So if we move to continuous calibration, we can do it deterministically, okay? And just to make sure, if you work with the minimax theorem, which is linear programming and it's polynomial kind of method, then your procedures are going to be stochastic. If you want to get continuous calibration, you need to solve fixed point problems, which is much harder, of course, but the payoff is that you are going to get deterministic procedures, okay? And that's very important for game dynamics, for example. See my talk of, my talk in the previous session of this conference, okay? And that's it, I'm done. Sorry that I'm gone over. I just thought that I'll finish with some announcement on successful economic forecasting. I don't know if you have seen it, but taking pride in our record, correctly forecasted 8 of the last 5 recessions. Okay, and it's a joke. Somebody took me seriously and didn't understand that. So thank you. I don't know if there are any questions. Everything was clear, everything was unclear. Or,
yeah, were there any questions in this room? I can ask a quick question. So I guess
sure.
like the basic kind of like decomposition you showed was kind of using the fact that you're working with like squared error, or I guess more generally this would probably work with like the Euclidean norm. I guess just a basic question is like whether you can do something similar for like, I guess, more general loss functions, like maybe if you have like a Bregman divergence or something like this.
Well, if it's decomposable, so Bregman divergences also have their own decompositions. So if you can decompose them neatly, yes, but it's, so for example, you try to do it with the L1 norm, it won't work, but you always know that if once you get it for the L2 norm, so you do the decomposition for the L2 norm, then whatever you get for the L2 norm, you get bounds then on the L1 norm for each one of the terms separately. That's the best way to proceed, yes. So you find a way where this is orthogonal, which is usually the L2, and then that's your starting point for the decomposition. Then, whatever nice properties you get for the L2 norm, of course, they transfer to any other norm. That's what yeah. But again, if you are, there are some certainties there, I must say. If you worry about bounds exactly and so on, then one may think they all work. And no, it's some things work neatly with the L1 norm, some things work neatly with the L2 norm. When you go to one, you lose something. But that's nice.
Yeah, no, that makes sense for sure. Let's see. Are there any other questions in this room? Oh yeah, Vidya.
You said a little bit at the end about calibrating with respect to multiple expert forecasters. I'm curious about whether you can, in any circumstances, get a calibrating result with respect to a continuum of forecasters, but something that's maybe well behaved. Maybe it's a convex set or something.
Look, if it's a nice convex set and you in some sense you beat the extreme points, I mean, you probably can beat their averages. I don't know. I mean, again, depends on what's the linear structure there. Yes, exactly. But no, I haven't thought about a continuum of forecasters. But where do you have a continuum of forecasters? No, I mean, it's again, it's there are probably technical problems doing that. I don't know, but conceptually, I mean, I don't see a problem, but technically, I'm sure there will be problems trying to do that. I should also say that our procedure, so taking our method, which is really you look at the joint binning of all the forecasters. So you have one bin for when forecaster 1 said 20% and forecaster 2 said 30% and forecaster 3 said 50%, that's one bin. When forecaster 1 said 20, the 30 for the second, 70 for the third, it's another bin. So the number of bins increases as the product of the number of individual bins, and that's not good, okay? So our procedure works, but in terms of error terms, it's not good. So in the appendix in our paper, we have another way of doing it, which gets still a log T over T error, okay, without increasing exponentially in the number of forecasters, which is a danger, okay? And that may be useful if you want to go to, say, a continuum, okay? So the simple way of doing it, the extension of that is when you have many, may become problematic in terms of the error terms.
Very interesting. I look forward to checking that out. Thank you.
Yeah. So as I said, look at the paper. I think it's we have it well done there. Or if you find an error, let us know. Or anything that is not clear, we'll be happy to hear about it. Yeah.
I think we've got one more question.
So maybe let me ask somewhat of a philosophical question. So I really like this work, as well as the sequence of works that preceded this one, and I think this is, this Calibeating concept is kind of one last piece of evidence that kind of demonstrates that calibration, is something that, in many circumstances, we can basically get like for free, quote unquote, if we wanted, right? And in this particular case, this decomposition shows some sort of orthogonality between some notion of expertise and just having calibration. And so clearly, from a human point of view, having calibration, means that, you can tell people, look, when I say this, that's what actually happens. But what do you think about the usefulness of calibration, just beyond sort of wrapping your predictor, which may already be like powerful and refined and accurate, into this nicer form? So what is the significance of calibration beyond that?
Look, in some sense you said it, yes. I mean, since calibration, you can get it for free. I mean, if you're not calibrated, I mean, something is wrong with you. Yes. Generating forecasts that are not calibrated, that's plain stupid. I mean, so again, up to these results, you could say, look, I can be calibrated, but then I'm losing on my expertise. Now we show you that you can keep whatever expertise you have and also get calibration. Okay, so why not? Okay. By the way, the forecasts are going to be different. The binning that I generate that we generate is different than the binning that you generated. Okay, so it changes the thing, but it preserves if the variance was small, if the refinement score was small, it's preserved. Okay, so that's a good thing. So the expertise is preserved. Again, at the general level, is calibration useful? Why do we care about calibration besides the fact that, it's a nice property, okay? So I'll tell you a story about a certain very big company that was using some forecasting procedure to know exactly what is going to be the demand for next month, in order to know how much to put in storage, something of that sort. Okay, they had to plan how much to order each month, and they were forecasting the demand. Okay, now somebody looked at it and said, "Wait a minute! I mean, these forecasts are not calibrated. Okay, I mean they are completely off mark." In fact, and looking at the historical data, there is a very easy way to improve them, not to get them calibrated, but very simple. Just multiply them by 0.7, and you're getting something that is almost calibrated, much, much better. Okay, so he succeeded in convincing the management of the company, and the company very happily, at some point switched, just use the same algorithm, but multiply the result by 0.7. Okay. Well, they expected, well, now we are going to get much better, since our forecasts are calibrated much better than before, we are going to make much more money. We're not going to have extra supply in our warehouses and so on. Turns out they started losing money. Okay, what happened? Well, what happened was something very simple. The guys that were managing the storage, they realized that the forecasts were not calibrated. And in fact, they knew that if the forecast comes as 100, they should not order more than 70. Okay. Now, when the forecast came 70, they ordered only 49. So they were short. Okay. So there's a miscommunication. So, in fact, we discussed this. If you want, read our paper in JP, our previous paper in JP just appeared last year on forecast hedging. We have a section on that we call the economic value of calibration, and forecasts that are calibrated decouple in some sense the forecasting part from the decision-making part. You don't have to know how the forecasts were arrived at. You don't have to know what they are. If they are calibrated, you take them at face value. And you make the decision given the forecast, which is really the right frequency, okay? Now, that's true, for example, for game dynamics, but it's also true in real life, okay? If the forecasts are calibrated, then you don't have to start saying yes, but you have to multiply by 0.7 or things like that, okay? So you know exactly what they mean and you don't care where they come from. So there is a big advantage to having calibrated forecasts for decision-making, okay? I don't know if that answers your question, but perhaps looking in our paper there, we have a couple of pages discussing this. Perhaps, something will strike you as relevant.
Thank you. Yeah, this was an amusing story.
Yeah, it's a true story, by the way. It's a true story. I know the person who was involved. I won't say which company it was.
All right. I think we'll stop there and go to the next break. We'll be back at 10:15 for the next talk. But yeah, so let's give another round of applause for Sergio, though. That was a really fun talk, and we're really glad you could join us.
Yeah, thank you. Thank you.
Thanks again.